All right, let's take a look at line notation. Line notation is just another way to represent a galvanic or voltaic cell. On the left side of the line notation, you have the anode components. You remember that's where oxidation takes place. On the right side in line notation, that's where reduction takes place. Those are the cathode components where reduction takes place. If I were to write the half reaction for oxidation of magnesium, it would look like this. Magnesium, that's rather sad looking magnesium. I don't know why it's so wrinkled. Maybe it's old. And it's oxidizing to magnesium 2 plus. That's aqueous. Oh boy, getting worse. Plus 2 electrons. Now that would be the oxidation half reaction for the left side of line notation. Magnesium oxidizing, and in this case, magnesium is an electrode. This vertical line here is a phase change. This is an aqueous solution in the anode compartment. The double lines here, that's the salt bridge. And then over here, we have the cathode components. That's the reduction half reaction. That would be aluminum 3 plus, aqueous, and this is reduction, so the electrons go on the reactant side, and that's producing aluminum metal, and it is a solid. And once again, this vertical line is separating phases, and the aluminum is an actual electrode in this voltaic cell. This is what the line notation represents: the oxidation in the anode compartment on the left and the reduction in the cathode compartment that's on the right. Here is some more line notation, only in this case we have inert platinum electrodes. These are only there to conduct the electrons into away from the anode compartment to the cathode compartment. And so they don't participate in the reaction. They are simply there to either release electrons in the case of the anode or accept electrons in case of the cathode. They're conductors. Okay, and then you have these two reactions. This is the anode, and again, that's the oxidation half. This is the cathode compartment. That's the reduction half. These are all dissolved ions in solution, which is why you need these inert platinum electrodes to conduct the electric current, because they're not doing chemistry. They're simply accepting the electrons from the chemistry. And the way this is written, we can see this as ClO3 minus aqueous is giving up 2 electrons. And so we have Cl4 minus 1. There's hydrogen ion in here. This is under acidic conditions. If you have looked at the videos on balancing redox reactions, you will get that. And there would be 2 electrons here because this is a plus 5 and this is a plus 7 oxidation state. So 2 electrons are being lost from the chlorate to become perchlorate. And then over here, again, this is just indicating that we have this reaction in an acid solution. It's under acidic conditions. And we have permanganate, MnO4 minus plus, and this is plus 7 to going to plus 2. So we're adding 5 electrons, and that's giving us the manganese 2 plus. Everything's in aqueous solution, and hoping you'll just accept that. Okay, as you can see, it's an aqueous solution. So this is the reduction half, this is the oxidation half. That's line notation, and of course this is the salt bridge in the center. Okay, for the following line diagram, what is the balanced oxidation half reaction? Keep in mind, that's what's happening on the left side. That's all you needed to know from that. And so that's aluminum losing 3 electrons to become aluminum 3+. So that would look like this. This is in the anode compartment. It is the oxidation half reaction. And just so you know, since this is manganese 2+, gaining 2 electrons to become manganese, this is the reduction half reaction. This is happening in the cathode, and this is happening in the anode compartment because it is the oxidation half. That one right there, and that goes with that, okay? This goes here. Okay. How do you predict which goes where? E of the cell must be positive to be spontaneous. Okay, so you have to have a positive E of the cell. You see us write this all the time. E of the cell is greater than 0. That is indicative of a spontaneous reaction. Spontaneous. It happens without outside intervention. Complete description, the cell potential, the balanced cell reaction, the direction of the electron flow anode to cathode, designation of the anode and cathode, nature of each electrode, and the ions present in each compartment. So here we have a reaction. Describe completely the galvanic cell based on the following half reactions under standard conditions. So the first thing we do is we find the highest cell potential, standard reduction potential, and that stays as it is as the reduction. The lower standard reduction potential, that's going to be the oxidation half, and we're going to flip that reaction. So this reaction gets flipped. Okay, so if I were to write this entire reaction, over here would be the oxidation, so that would be Fe2+, giving up an electron to become Fe3+, plus 1 electron. That would be the oxidation half. That would be in the anode compartment. Over here in the cathode compartment, you have silver plus 1 plus an electron to become silver metal. And let me just tell you that this is where reduction is taking place, and this is the cathode. Now, typically, when we draw our cells, we'll put the anode on the left, cathode on the right, but that is not, that's merely convention. It is not hard and fast. You can actually have cathode on the right and anode on the left. Just remember that anode is where oxidation takes place. Cathode is where reduction takes place, and the electrons always flow from anode to cathode in a voltaic cell. Okay? All right, and they do it spontaneously. Oh, well, here is our reaction, and they did put the cathode on the left side, the anode on the right side. Again, here is where the oxidation half reaction is. In the anode, you can tell that it's oxidation because the electrode's on the product side. Over here, you can tell that this is the cathode because the electron's on the reactant side. It's being added to a species. The electron flow is always anode to cathode. That's the way that it rolls. Okay, this would be the line diagram using an inert platinum electrode for the anode compartment, because both of these are in aqueous solution, and then for the silver ion being reduced to silver metal. The silver metal is actually an electrode on this particular reaction. Free energy with respect to cell potential. This is our equation for relating delta G from chapter 18, the change in Gibbs free energy under standard conditions, is equal to minus NFE. N is the number of electrons that are transferred. F is Faraday's constant, 96,485. And in this context, it's going to be joules per volt mole, and then times E of the cell, which we have been calculating. And you have a minus sign out here. So this is the number of electrons that are transferred times Faraday's constant times E of the cell. And so there are other units. There are coulombs per mole of electrons. There are also joules per volt times moles of electrons. And that's the case that we would be using it with delta G equals minus NFE. All right, and that the standard cell potential. All right, let's calculate delta G naught. Using the following half reactions, calculate delta G naught for the reaction below and predict whether the reaction is spontaneous. So the deal on delta G naught is, first of all, we have to go ahead and calculate E of the cell. So let's decide which cell, this is the higher cell potential. That's for copper 2 plus, and they've given us the reaction. So we know copper 2 plus is going to be reduced. Iron's going to be oxidized. We've got a plus 2 here. We've got a 0 oxidations here. This is 0. This is plus 2. Copper is being reduced to copper metal. That's a reduction. And by the way, that makes copper 2 plus the oxidizing agent. You can practice all of this stuff no matter what kind of problem you're doing. Iron is going from a 0 to a plus 2. That's a loss of electrons, so that is oxidation, and that makes iron the reducing agent. Never pick anything from the product side as what gets oxidized or reduced. You use the product side to determine what happens on the reactant side. So this is going to be our reduction half. This is going to be our oxidation half. So cell potential, E of the cell under standard conditions is E of reduction, 0.34, plus E of oxidation. Since this is oxidation, we're going to flip this, and when we flip it, we change the sign, so it's now 0.44 positive. And so we'll just add that up. That's going to be 0.34 plus 0.44. And that gives me 0.78. So the standard cell potential is 0.78 volts. So let's put it together. Let's go ahead and calculate delta G. I'll do it right here. Delta G naught is equal to minus, and the number of electrons transferred, since the number of electrons being gained and the number of electrons being lost is the same in the half reactions. I've had students think that you needed to multiply 2 times 2. You don't. It's 2 electrons. So if these two numbers are the same number of electrons being lost or being gained as being lost, then N is equal to 2 moles of electrons. So that's what we're going to have up here. 2 moles of electrons. Now Faraday's constant, 96,485. joules per volt mole, and then times the cell potential, which we figured out was 0.78 volts. Let's just make sure the units cancel. Moles of electrons cancel. Volts cancel. Now this is going to give us an answer in joules. What do we usually report delta G in? Kilojoules. So once we get our answer here, we need to divide it by 1,000 joules per kilojoule to get it into kilojoules, which is the way we normally report delta G. So delta G naught will equal, so let me go ahead, minus 2 times 96,485 times 0.78, and that gives me 1.51, minus 1.51 minus 1.51 times 10 to the fifth joules, which we're going to divide by 1,000 joules per kilojoule. And what that gives me for a delta G naught is a negative 150. Let's see. Divide that by 1,000. Yeah, that gives me a negative 151 kilojoules. And that would be delta G naught. Okay, so delta G naught is equal to minus NFE. Remember this, delta G equals minus NFE. Okay. All right, this is just a little diagram to help you convert from one unit to another. Handy to remember that delta G naught is equal to minus NFE naught. Delta G naught is also equal to minus RT natural log K. And so I could actually get K from delta G naught. You might remember this. This is going to be minus delta G naught divided by RT. That's actually an exponent. To get rid of the natural log, we take the E of that. So we can go back and forth using between delta G naught and K using this expression. This is a piece of the Nernst equation, which I will show you in a little bit. And then you've got delta G naught equals minus NFE. So hold on to that. All right. So size matters in terms of delta G, and sign matters. So if we're talking about a spontaneous reaction under standard conditions, delta G naught will be less than 0, which means that E naught will be greater than 0, which means that K, the equilibrium constant, will be greater than 1, and that would be a spontaneous reaction. A non-spontaneous reaction, delta G naught, would be greater than 0, positive. That would make E naught less than 0, because if you remember, delta G equals minus NFE. So if E is negative, then delta G, because you have a minus times a minus, delta G will be positive. If E is positive, then because you have a minus times a positive, you get a negative, delta G will be negative. And then K is less than 1 if E naught is negative. Let me show you a diagram that I think helps you to get these ideas. So I know that may be a little bit small. It was the best that I could do under the circumstances. But here's the deal. Remember, under standard conditions, Q is equal to 1. That's Q under standard conditions, products over reactants. Now, if a reaction is spontaneous in the forward direction, so let's just say that our reaction is A in equilibrium with B, and our reaction is going forward. Well, if the reaction is headed in the forward direction, A is disappearing. It's getting smaller. The product B is increasing. It's getting larger. And remember, we're starting, if we're under standard conditions, where Q is equal to 1. Both A, reactant A, and product B are 1. But product B is getting bigger. Let's say product B goes up to 2, and product A goes down to 0.5. Now you have 2 divided by 1/2, and so you get a number that's greater than 1. You started at 1, but now you have a number that's greater than 1. So if the reaction is spontaneous forward, Q is less than K, delta G is less than 0, E is greater than 0. And so what's happening is you have, if this is the case, is delta G naught is less than 0. And that's when Q is equal to 1. So K has to be greater than 1 if delta G naught is less than 0, because from standard conditions, where Q is equal to 1, the reaction is spontaneous forward, generating more product, consuming reactant, and making K greater than 1. If we go over to the other side, and let's say delta G naught is greater than 0 over here, delta G naught is greater than 0, then it's non-spontaneous forward, it's spontaneous in reverse. So under that set of condition, what's going to happen? Okay, so instead of, oops, all right, let me grab a pencil over here. Instead of having the reaction run in the forward direction, the reaction is going to run in the reverse direction. And remember, you start under standard conditions with Q equaling 1. That means B and A are both 1. And in this case, B is going to get smaller because the reaction is running in reverse. That means that A is going to get larger. And so what you wind up with is, let's say, 0.5 for our product and 2 is our reactant, which gives us a number that is less than 1. Okay, so if delta G naught is greater than 0, the reaction is spontaneous in reverse from standard conditions. That means that E naught is less than 0, non-spontaneous forward, spontaneous in the reverse. Q is greater than K, delta G is greater than 0, E naught less than 0. And finally, let's get over here to equilibrium. What's happening in equilibrium? Well, delta G is equal to 0, Q is equal to K, the cell potential is equal to 0. You have a dead battery. And the reaction is non-spontaneous in either direction at equilibrium. Remember that. At equilibrium, the reaction is non-spontaneous in either the forward or the reverse direction. Okay, that's the best I can do on that. All right, effective concentration. How does the cell potential vary with concentration? Standard conditions include solutions, as you know, with 1 molar concentration. When a concentration is varied, we can use Le Chatelier's principle to predict the effect. Now, here's the deal. If the reaction is running forward, then E of the cell is stable, and if you can cause it to run even more forward, you might increase the cell potential. If the reaction is running in reverse, or it is the cell is discharging, if you boost some product, it's going to run in reverse based on Le Chatelier's principle. That will decrease the cell potential. Okay? All right, so here's the case. For the cell reaction, 2 aluminums plus 3 manganese plus 2 yields 2. Let's analyze this real quick. We got 0 oxidation state here, plus 2 here, plus 3 here, 0 oxidation state here. Aluminum is being oxidized to 3 plus. That makes aluminum the reducing agent. Okay. Manganese 2 plus is being reduced to 0. That's reduction. And that makes manganese 2 plus the oxidizing agent. Oxidizing agents get reduced, reducing agents get oxidized. Okay, so here's the deal. And by the way, 6 electrons are being exchanged here. The way you can tell is 2 times 3 is 6, and 3 times 2 is 6. So 6 electrons are being transferred. That might come in handy somewhere. Okay, let's predict whether E of the cell is larger or smaller than E of the cell for the following cases. So remember, under standard conditions, this is what we're saying. Under standard conditions, the manganese is 1. Let me erase some of this stuff, make it a little easier to see. We did what we needed to do here. Okay. Okay, under standard conditions, this is a 1, this concentration is 1 molar. And this concentration is 1 molar under standard conditions. If we change these concentrations and we make the aluminum 3 plus, we raise this concentration to 2 molar, keeping the manganese at 1 molar. That is going to shift the reaction in the reverse direction, and that will lower the E of the cell. So this will be a smaller cell potential, okay, because the reaction is shifted back toward the reactant side. On the other hand, and let me erase a few things. Oop, that's not what I intended to do. Okay. Okay. Let's go back to it. For B, this remains at 1 molar, but we're going to up the concentration of our reactant to 3 molar. So we've increased a reactant. Le Chatelier says it's going to shift in that direction, and that's going to make E of the cell a larger value. This will be bigger. Bigger E of the cell because the reaction is more spontaneous in the forward direction, or the equilibrium shifts it to the right towards products. All right, so that's how you analyze that. The Nernst equation gives the relationship between cell potential and the concentrations of the cell components. Now, this is the version of the Nernst equation that you can use for any particular temperature. E equals E naught. This is a non-standard cell potential. E naught minus RT over the number of electrons transferred times the Faraday's constant times the natural log of Q. Honestly, there have been very few problems in my chemistry career where I've not been able to use this. Even when it wasn't exactly at 25 degrees, you're going to get a fairly predictable result. And the Nernst equation is provided on the exam. And so N is the number of electrons transferred. It's the number of electrons transferred. We just talked about that. If you're going to use this version, note this is log base 10, not the natural log. If you use this version, it's perfectly fine. It's a little more complicated, a little bit more to remember, but this version is just fine. Just remember you're using log, not ln. And then Q you have to calculate. So, oops, I don't know what happened there. Okay, let's go ahead and work a problem. So calculate E of the cell for the galvanic cell in which is based on the following two half reactions when silver ion is 1 molar, hydrogen peroxide is 2 molar, and hydrogen ion is 2 molar. Okay. First of all, the number of electrons transferred is pretty easy. You've got 2 electrons in what is going to be the reduction half reaction, and then you have 1 electron in what is going to be the oxidation half reaction. This is going to be the oxidation half reaction because it is a smaller reduction potential than the hydrogen peroxide. So that's what we've got. So the number of electrons transferred, N, is simply 2 times 1, or 2 moles of electrons. So that was easy. The problem is we need coefficients for everything. Now, we know we need to multiply this by 2 and this by 2. And the problem is, I don't know if we have a problem here. I think this is actually going to work out pretty well. Let's just see. So I'm going to flip this reaction. So I've got Ag solid plus H2O2. This is aqueous, so it goes in our equation. And then we've got a couple of hydrogens. That's important. And we know we're going to have 2 electrons here. And so this is going to be 2 of these. That's going to give us 2 of these. Ag plus, and then finally we got a couple of waters out here, but the waters don't matter. They are a pure liquid. They don't count. This does. Aqueous. Okay, let's just see if it's got 2 silvers, 2 silvers, 2 hydrogens, 2 hydrogens. That's 4. 2 times 2 is 4. 2 oxygens, 2. We are balanced, ladies and gentlemen. So you know what that means? We can calculate Q, which we need. So here is Q. Q is going to be products. So that's going to be our silver ion concentration squared divided by our hydrogen peroxide concentration times our hydrogen ion concentration squared, because its coefficient is 2. So let's just plug everything in, figure out the Q, and then let's plug our values into the Nernst equation. So our silver concentration is 1 molar. So this is 1 molar. It's squared, but that's not going to change anything. Our hydrogen peroxide concentration is 2 molar, but its coefficient is 1. And then finally, our hydrogen ion concentration is 2, and we need to square it. So let's go ahead and figure that out. So that's just 1 squared, which is 1, divided by 2 times 2 squared. And that gives me 0.125. So that is my Q, 0.125. Now I have everything I need. I don't have my cell potential. Let's go ahead and get that. So E of the cell under standard conditions will equal the reduction half, which is 1.78, plus the oxidation half, which is a minus 0.80. All right, let's see what we got. So that looks pretty easy. 1.78 plus a minus 0.8, which gives us 0.98. So our standard cell potential is 0.98. Okay, and that's volts. Now, here is the Nernst equation that we're going to use. E of the cell under non-standard conditions is equal to E naught minus 0.0591 divided by N, and it's log base 10 log Q. Let's just plug in. E is equal to 0.98 minus 0.0591 divided by 2 moles of electrons, and then times the log of E of the cell, which is not E of the cell, the log of Q. Whew! It's been a long night. I actually did this recording already, and unfortunately, my computer dropped it, so that's why I'm doing it again. So long day, and I had Thanksgiving dinner with the family. I hope you had a great Thanksgiving. So here we go. So 0.98 minus 0.0591 divided by 2 times the log of 0.125, and that gives me a voltage of 1.01 volts. So the non-standard E of the cell is 1.01 volts. Hopefully that showed up. Let me put it over here just to make sure. 1.01 volts. Okay, that is using the Nernst equation for non-standard cell potentials. Consider the electrochemical cell based on the reaction. 2 hydrogen ions plus 10 solid produces 10 plus 2, so 10 is being oxidized to plus 2, then you got H2 gas. Well, here's the deal. The gas counts, the concentration in aqueous solution counts, the concentration in aqueous solution counts. The only thing that does not change cell potential is a solid or pure liquid. So increasing or the addition of more tin metal will not change E of the cell. It will not change E of the cell. Okay? All right. Nernst observations: as the cell discharges and the current flows from anode to cathode, the concentrations will change and E of the cell will change. The cell will spontaneously discharge until it reaches equilibrium. That's where Q equals K, E of the cell equals 0. You have a dead battery, and any organism that has an E of the cell equal to 0 is deceased. Real-world application: batteries, plating, protecting metals so with more active metals so that they don't corrode. Batteries, self-contained power sources that consist of one or more voltaic cells. The lead-acid battery car is what you have in your internal combustion engine car. Lithium-ion batteries are what you have in your electric car, more than likely. You've got alkaline cells in your calculators and lots of different devices. If you go into space, you're going to use fuel cells. The advantage to fuel cells is just hydrogen and oxygen producing water, and you have electrons transferring. And so you're oxidizing hydrogen, you're reducing oxygen, you're making water and electricity. Hopefully we can get these into cars. The problem is hydrogen storage. So there's got to be some safe way to store hydrogen before fuel cells will be big players in internal combustion engines. Corrosion is a redox process. We can actually use protection called cathodic protection. We can, let's say, paint or use on ships, they use these big zinc bars and they bolt them to the hulls of iron ships. And the zinc is a more active metal than the iron, so the zinc corrodes and the iron does not. We call that cathodic protection. You can also just paint over metals that have a tendency to corrode to try and block oxygen. But here you have zinc, which is a zinc coating over iron to so that the zinc oxidizes rather than the iron. And so you have cathodic protection of water pipes in the ground. You just have more oxidizable metals that are attached by wires, and it's literally sacrificing itself so that your metal pipes don't corrode. Okay, let's talk about electrolysis real quick. Electrolytic cells uses an electrical energy to produce a chemical change. Electrolysis is forcing a non-spontaneous reaction to occur. How do you do that? You force a current through a cell to produce a chemical change for which the cell potential is negative. A cell potential that's negative is non-spontaneous, but we're going to force it to happen by providing a current that we're going to force into it. So we're making a reaction run in reverse by providing the electrons that force the reaction to occur. And this is how you do things like electroplating. Your grandmother's silver, sterling silver, is done in this process. So comparison of a galvanic cell has a negative anode. Electrons flow from the anode to the cathode. The cathode is positive. You've got your salt bridge. But when we look at an electrolytic cell, it's almost the same. Electrons still flow from the anode to the cathode. The only difference is this is a non-spontaneous reaction that we're using a power source to drive, and that the anode is positive and the cathode is negative. So in an electrolytic cell, the anode is positive, not negative, as it is in a voltaic cell. The cathode is negative. In an electrolytic cell, not positive as it is in a voltaic cell. Voltaic or galvanic cell, anode is negative, cathode is positive. Electrons flow from the anode to the cathode. Electrolytic cell, electrons still flow from the anode to the cathode. It's just that the anode is positive now and the cathode is negative. All right? That's the big difference. All right, let's work a problem using this. So what mass of cobalt metal can be produced from cobalt 2+ in solution in 1 hour with a current of 15 amps? So first thing you want to know is 1 amp is equal to 1 coulomb per 1 second, or just coulombs per second. So if I've got 15 amps, that's 15 coulombs per second, okay? So we're going to need that. We're also going to need Faraday's constant, which is 96,485, and this is where we're going to use coulombs per mole of electrons, all right? Those units for Faraday's constant. Remember, when we were doing delta G naught equals minus NFE, we were using joules per volt mole. Here we use coulombs per mole of electrons. Same number, different set of units. All right, so here we go. So I want to know how many grams, let's say, of cobalt. And I'm running this electrolytic cell for 1 hour. Every 1 hour has 60 minutes. And then every 1 minute, 60 seconds. Now comes your amperage in coulombs. So every 1 second is equal to, in this particular case, 15 coulombs. Because remember, 15 amps is 15 coulombs per second. Okay, and then Faraday's constant, 96,485 coulombs for every 1 mole of electrons. And the other thing we needed to look at was cobalt. So we're reducing cobalt, which doesn't want to be reduced. Okay, it's got a negative cell potential. We're adding 2 electrons to cobalt plus 2 to make cobalt solid. So 2 moles of electrons, that's a 2. 2 moles of electrons for 1 mole of cobalt, and then 1 mole of cobalt weighs, oh my gosh, I don't know how much. I don't know the molar mass of cobalt. I'll have to go look it up. Hold on. All right, I'm back. 58.93 grams. Okay. So here we go. Let's check the units. Hours over hours cancels. Minutes over minutes cancels. Seconds over seconds. Coulombs over coulombs. Moles of electrons over moles of electrons. Moles of cobalt over moles of cobalt. So it all looks good. Let's go ahead and calculate. So 1 times 60 times 60 times 15 divided by 96,485 divided by 2, and then times 58.93. And I get, looks like 16.5 grams. So 16.5 grams of cobalt from running this electrolysis for 1 hour at 15 amps, which is 15 coulombs per second. All right, let's see if we got another one in here. Yes, we do. A chromium-3 solution is electrolyzed. We're just putting in an electrolytic cell. We're forcing a non-spontaneous reaction to occur using a current for 7.6 amps. Let's go ahead and break that down. 7.6 amps is 7.60 coulombs per second. Okay. We got running it for 2 days. They're going to ask me for chromium. I'm going to go ahead and find out chromium's molar mass right now. Looks like it's so... Okay, I forgot to turn the recorder back on, but let me just show you what I've done. I went and looked up the molar mass of chromium, which is 52 grams per mole. A chromium solution, electrolyzed 7.60 amps. I set it up, X grams of chromium. I want you to remember 1 hour is equal to 3,600 seconds. Chromium 3 plus 3 electrons gives you chromium metal. So here we go. 2 days, 1 day, 24 hours. 1 hour, 3,600 seconds. 1 second, 7.60 coulombs. 96,485 coulombs per mole. That's Faraday's constant. 3 moles of electrons reduces 1 mole of chromium 3 plus. 1 mole of chromium weighs 52 grams. plugging it into the calculator. Gosh, I hope this worked. 2 days divided by, 2 days times 24 hours times 3,600 seconds times 7.60 coulombs divided by 96,485 Faraday's constant divided by 3 times 52, and I get 236 grams of chromium. 236 grams of chromium, and that's the answer to that. I hope there's nothing else. Oh my gosh, what was your favorite topic in Chemistry 1342? I cannot possibly imagine. But it's late, and I'm going to say good night. Hopefully you watch the video before the lecture. It'll help.